Thank you, Chris, for a nice introduction. It's really my pleasure here, and happy Chinese New Year. Today, I would like to share my research about how to take a step toward building spatial intelligence, even with limited data. We live in a, let's see, 3D world. So in a lot of these applications, including robotic, autonomous driving, 3D visions, graphics, and physics simulation, all of that deal with 3D data. So being able to understand and analyze 3D data is very essential. So it's fair to say that center at the middle of these applications is the ability that we call spatial intelligence. So for me, spatial intelligence is the ability that can synthesize and analyze 3D shapes, especially connecting 3D with other modality. Let me give you an example. So for example, 3D reconstruction can be think of connecting images to 3D. You take image as input, output in 3D shapes. This is a type of 3D synthesis task. And physics simulation can be thought as a 3D analysis task, where the input is a 3D cell together with some other physics parameters, and then the output is potentially an image that contains the physics parameters needed in order for you to understand the underlying shapes. And a lot of application that we care about requires a synthesis, require together both the synthesis and analysis application. Imagine that you want to build a home robot. They need to reconstruct the house and analyze the environment in order to navigate through it. So in the middle is this, the ability to do both of these tasks well is very essential. So human has very strong spatial intelligence. One of the easy ways to gauge the test yourselves is to look at this very typical called mental rotation problem. So the idea is, if you look at the shapes here and ask like, which of the following shapes is a rotated version of the shape on top? So for me, in order to solve this problem, I first do a single view reconstruction. I look at these shapes, I create a mental picture of the 3D shapes, and I manipulate this mental picture, take different views of that mental 3D shapes, trying to match one of the answers below. So implicitly, I already performed this synthesis and analysis steps underneath. So just to make sure everyone's awake, who thinks, let's give a raise of hand. Who think the answer is A? 1, 2, 3, 4. So all of us have spatial intelligence. At least we are able to get to the answer in some way. So I'm going to keep not release the answer. So even until the end. So you need to stay with me. Okay. So this seems like a very toy example, but in fact, we are able to take this ability and create something that's very complex. So this is a fast forward video of an artist, a skillful Blender artist trying to create a lunar dragon. So as you can see, it used the tool of Blender to create 3D shapes, look at the shapes from the GUI image, repeat the synthesis by analysis steps in order to create a very complex product at the end. And in fact, not only in graphic editing, but also in other applications in science engineering, including mechanical design and even building real-world objects like civil engineering, the ability to understand and synthesize 3D shape is very essential. But all of these are still very manual process. You can see that you need a user behind the screens to manipulate the Blender. You need a lot of worker on site in order to build the building. Would it be nice if we can build intelligent agents to help us make some of these decisions and to facilitate the complex task? So it's very challenging. So first problem that we run into is like this, what I call a death by 1,000 cut issue. So as Professor Ray put it very well, so the death by 1,000 cut refers to the challenging where each of the instance might be solvable, but in order to solve the whole complex problem, you need to solve a whole variety of the instance. So let's take a look at this this task. Imagine that you want to start with the coarse dragging, and then you want to end up with a target image with some very cool animation render. So inside this process, you need to go through a very complex graphical editing pipeline. So you artists start with geometry modeling, figure out how to model appearance, and then figure out how to model animation. inside each of the pipeline, the artists need to be master of a lot of tools like sculpting and then remeshing it. And many of the decisions made here will affect the results far down the pipelines. And each of those, inside each of these algorithms, the artists need to decide the parameter to use the algorithm and and then need to render in multiple views. So it's a very repetitive process, and the artist has to be very skillful to be good at a lot of different tasks. So this gives you a sense of this is actually a huge variety of problem setups that we need to tackle in order to finish this pipeline. So here's the question. Don't we already know some potential solution to this? The same issue come up in machine learning, NLP. So process language is a death by 1,000 cut problem. How do they solve it? They train a large model. They train a very large model that can be specialized later on to be good at a lot of things. But training a large model that's good at 3D is also very challenging. First, we do not have that many 3D data. So on the left, I show how much data we have that people use in order to do the pre-training for foundation model in vision and language. But on the right-hand side, I show that the existing largest data set in 3D contains about 10 million shapes, which is like drops in the ocean compared to all the data in the internet. Just to make it a little bit more challenging, these shapes are not stored in one unified representation. So there are different 3D representation people use for different applications. And this further divides the available data and also make training one unified model that works for all a little bit more challenging. So apparently, this brings us to the key question that I want to discuss today. So apparently, we can't leverage pure machine learning pipelines because we don't have a lot of data given all the data blockage. And writing down equation to solve this end-to-end pipeline is also challenging given the variety of this of the problem scale. So what are some of the ways that we can take a step? So let's first look at what we have. So in order to connect multimodal data with 3D, first, we already know there is a lot of foundation model that's built to understand multimodal data. So like GPT-4V and the new one that come out like yesterday, journals, all of them are able to do a variety of tasks involving vision and language, but they are restricted to operating in the space of image and text tokens. On the other hand, we have decades of developments of computer graphics and vision. All of them has provided excellent modeling tools. What I show here are like those graphical editing platforms. There are a lot of buttons inside. Each of them are great modeling algorithm that's able to perform specific tasks well. Even though there is no mechanism to connect all of them, it still requires the human brain behind the scene in order to use this model well. But there are actually a lot of solutions for specific tasks. So what I'm hoping to explore today is, are we able to find a bridge in the middle that's able to connect the powers of being able to perform a little bit of more complex and variety of tasks versus the power with the power that's able to handle 3D. So in fact, this is, I explore many different representations that's trying to connect the machine learning worlds and the computer graphic worlds. Today, I'm going to share you one of the few exploration that makes. So let me show you in the high level. Imagine that I want to build a rather general analysis, synthesis pipeline, taking multimodal data like language and image and predicts 3D. So what we have right now is we know that if we can write codes in this graphic engine, imagine that you can write Blender codes pretty well. We can run Blender to build us the 3D scene. So now the question is, are we able to find a way to write pretty good Blender codes? So actually, it turns out that we can potentially connect for example, the visual language data to Blender code potentially using visual language models because they are able to write codes pretty decently. So this will allow us to potentially connect the dots between the visual language model and all the tools that we have in graphical engines. So imagine that I want to analyze the 3D data. So here's one way. We can take these 3D shapes, render them into images. We know how to render different 3D features, the depths, surface normal, and we know how to render in different views, and we can choose the views that can reveal more information and less. And all of that turned into a representation the vision language model can potentially understand. So taking this pipeline together, so now that we have one site potentially a model that's able to code different code for different graphical engine, potentially very complex code. On the other hand, we have a model that's able to take a look at what we build, render from a graphical engine, and analyze them by, for example, answering your question, telling you how to improve. We can put this back to the loops into a synthesis by analysis pipelines. And the hope is we would like to see that we can potentially repeat this pipeline to achieve tasks that require multiple steps. So today I'm going to talk about 3 works. Each of them are example and related to building toward these pipelines. So I will first talk about how to create specific types of 3D shapes, 3D garment objects using this idea, and then how to evaluate text to 3D generative model using the evaluation pipeline that I described, and finally a work that connect both of them in order to do Blender, to edit Blender scenes. And yeah, welcome to interject with any questions. I'd like to make this more a discussion as well. Yeah. Okay, without further ado, let's dive into the thing about how to generate garments. Yeah.
The way Blender works, is it, do they work in this like the full scene scale, or is it more object based?
So good question. So Blender works on more of the scene or object scale. So I think the deeper question is like, how do you differentiate from scene and object? Yeah, so I mean, in object-verse, there is also this kind of room, which to a lot of us looks like a scene, but it can also be a object. So I think it kind of depends on how we look at that. So I do see that people use Blender to build very complex scenes. So I think there is a way to work on the complex scene level. Yeah, but what I use Blender as an example in the later of the talks, but it's not some of the method that I described is not restricted to Blender. Yeah, okay. So garments, okay. 3D garment happen to be perhaps one of the commonly used shapes. So everyone wears something every day, I hope. So I think it's actually perhaps one of the most used 3D objects that we in our real life. So how do we actually make and represent garments? So underlyingly, garments are commonly represented in a representation called sewing patterns. So imagine that you take the t-shirts and unseam and connect all the seams together. You will see a collection of 2D panels. So they are 2D shapes, as well as an instruction of how to connect this 2D panel into a 3D garment. The reason that sewing pattern is actually a very interesting representation is because it contains the challenge of a lot of other 3D representation like mesh. So it has the combination of discrete and continuous structures, and being able to, and it can also get geometrically very complex. So in this work, what we are hoping to do is to build a neural tailor. The idea is like when you go to the tailor, you are very likely to communicate with it using language and text. Like sometimes you will sketch, sometimes you communicate with language. Would it be nice to have a agent that's able to be your personal tailor, outputting a sewing patterns? So if we would like to apply the traditional like machine learning paradigm, so the number one thing that we'll do is collect a bunch of data, right? So we collect language description and image of the render of the garment and the sewing pattern itself. It turns out the largest data set we can get is about 100,000 pairs. So this is probably not enough for us to train a model that's able to understand complex language and vision interaction from scratch. So what we want to do is, instead of training from scratch, we want to leverage the existing large language, vision language model. So we know that there are a lot of open source models that can take language and image as inputs and outputs language and code. So that they are able to output a sequence of tokens. So what we're hoping to do is to connect the dot between this sequential representation with a 3D garment representation by building a garment tokenizer. So what is a garment tokenizer? It is a bidirectional mapping between the sewing pattern 3D representation and a series of tokens. So in order to think about it as like describing a language that translates between 3D shapes. And yeah, so in order to do that, we need to first define what is in the language. So we are going to define 3 types of vocabularies. I'm going to tell you how each of those vocabulary works. by going through this example of tokenizing one garment here. So each of the sewing patterns can be first broken down into a series of 2D panels, as I show you. So the first thing we want to do is, since each of the panels might require different amount of length in order to describe them, so we would like to first wrap it with the start and end panel tokens, so that in that case, we can zoom into each of the panel without worrying about all the others. So now let's zoom into this panel. How do I describe this panel? So this panel can be thought as a series of drawing instructions. So in order to create these shapes, I will first draw the curves, the straight line, another curve, and another straight lines. So what we can do is we can describe each types of drawing using different tokens in the vocabulary, but this is not enough because there are different ways to draw the curve, as well as like different ways to draw the straight line. So we further paired the types of curves and strokes with the continuous parameter that's needed in order to describe them. So you can think of this pair of class and continuous parameter as one token. It's like an augmented language. And finally, we also need to give the instruction of how to connect them together. So here, what we are doing is for each of the each of the line that we draw, we give them a stitching tag. So how do we use the stitching tag? So imagine that we have a different garment. So this, different panel. This is the front of the skirt. This is the back of the skirt. So the lines that has the same tag. So this is tag number one will be stitched together in 3D. And the one without the tags will be ignored. So this way, we are able to provide a series of instruction to connect different panels together. So finally, this allows us to take a 3D garment, serialize it, but this is still not the language that Lava or those vision language model is able to output. They output code and English. What do? We can fine-tune the Lava to speak the language using the next token prediction loss. So far, all of these are standard operations, but remember, we also have continuous variable attached to some of these tokens here and here, right? How do we predict this continuous variable? So if we look at a standard transformer architecture, so the ways that the token are consumed is the token will first go through a token embedding to create a latent code of fixed dimension. That latent code goes through a large transformer to output another latent code with the same dimension, which goes through the classification head. What we do is we think of this token as not only a class, but also connected with a series of continuous number that used to parameterize the class. So what we do in the beginning is I would take this set of number, pass it through a positional encoding, encoded with the sinusoidal positional encoding, and then add these two latent codes together before passing into transformer. And at the end, before we output it into the class head, we also take that latent code, pass it through a regression head. So the regression head will regress the fixed number of variables. Question? Mm-hmm. Sorry, I might not understand. What do you mean by automatic way? Yes. Right. Right. So basically the way tokenizer work is like it's defining a ways to store the data in a different representation that the transformer is able to understand. So what we do is like we take the set of garments, we design the tokenizer. So we design it in this way that I described, and then I go through the whole data set, translating all of these garments into a series of tokens. And then during the training, they will only look at this series of tokens. Yeah. So that's automatic. Yeah, that's all automatic. Yeah. Costa?
I really love the idea. Now, for example, if a segment has a hole, for example, because you chose a linear representation of the shape. Right? Linear representation might apply only to a genus.
Yeah, very good question. Right. I think the high-level question is like, how do we represent geometry with more complex topology? So I think the ways that, imagine that there is a holes in the middle, like I want to represent a donuts, right? So what happened is they will actually cut it in half. So break it down into all genus 0 and then represent because once we cut it, we know how to sew it together. So we end up with more panels, but yeah, we don't all, like it's kind of hard to think about how to represent all the holes, but we basically just cut it down to represent all the small pieces and glue them back together to form holes at the end. Yeah, I think that's like what happens in most of the.
I still didn't understand automation. I must say there was a field that died completely called syntactic pattern recognition.
Oh, yeah.
There's even a book by Kay called Syntactic Pattern Recognition, and it was doing exactly this. And it was doing it for a lot, actually, of one-dimensional signals like EKG, for example, or and as soon as statistical techniques came out, died completely because the segmentation was considered as the hardest problem to do. So when given like a continuous contour, where exactly to segment in order to put a token there. So how is this done?
Yeah. So how do we decide, for example, where to, like for example, how far do we draw the lines, right? So remember, tokenization is a way to represent the data. So in our data set, we will see millions of garments that people design, and they already decided on like where to put the final, where do you put the final endpoints and how much curve they have. So what we are doing here is to translate it into something that the transformer is able to understand. But I think that what you're asking is actually a deeper question where, I mean, for example, if I have garments, right, how do we want to break it down into, for example, something that like a sewing pattern and then represent it, right?
Segment. I mean, it's the fashion houses.
Right.
But even a segment. Segment is when you're getting it from a drawing, right?
Yeah.
Like in the translation, how is it translated to a sequence of tokens?
Yeah. Oh, I see. So they might be in a different order, right? There are different order to draw it. Okay. So imagine that there is so in the inputs of this tokenization, right? We were given a SVG that's already like drawn. That we already have a lot. Right. It's not a random curve. Yeah. So there is the data set where the garments are represented by a standard language. Yeah, right, by segments. Right. So this is, and of course, I think expanding this language to capture, for example, more complex garment is ongoing research, and I think that's still a very interesting geometric questions. Yeah, right. I hope that clears up. Yeah, cool. So so we are here, so we know how to encode contingents of variables and predict them. And doing inference, we just take the predicted one, so this tuple, put it up front, and then we can do the autoregressive generation. Just to have some of the results. So this one model is able to perform multiple tasks, including taking text and image into garments, image to garment, so doing garment reconstruction, as well as garment editing. So the idea is that you want to take this garment and then give an instruction of how do they want to edit, and they will give a edited version where they create this asymmetry design in both the sleeves and the front, as well as like text to garment, like if you describe the scenes. And one other thing that is interesting is like, since we're predicting sewing patterns, so all of this can be stitched together and readily fabricable and simulatable fashion. So all of this, we take our patterns, we sew them together, put it into simulator, and it's ready to go. So this kind of hopefully give you a taste of like we can potentially repurpose the visual language model to predict a form of codes that translate into the 3D shapes that we are interested in. And we can even handle some of the complex structure that include both discrete and continuous parameters. And the idea is to augment your tokenization to predict tokens with a pair of the class as well as the continuous variables. So now we can, we've seen a lot more 3D generative model now. So now the one question that I start to ask is like, how do we tell which of the 3D shapes that we generate is better? So in fact, I would say that since 2022, I've seen a super blossom of like 3D generative model from text. Since the publication of Dream Fusion, then there have 2,000 citations, and this is just a snapshot of the bunch of paper that the week before I submit the CVPR. So given so many generative models, how do we know that which one performs better? How do we know that we are making progress? So it turns out that perhaps one of the most used and most potentially trusted way is to do a user study. So here's how it works. So you will hire a potential evaluator from Mechanical Turks, and the evaluator will write a text description to send to 2 different 3D generative model behind the wall, so it doesn't know which one is which. The 2 3D generative model will return the shapes that they generate, and the evaluator will be asked which of the 3D shape is better. So it turns out that we need to do this a lot of times in order to get some stable statistics. So usually this is a very expensive process. And every paper needs to do that during the time is kind of like a lot of manual labor. So I'm trying to ask the question, so are we able to automate part of this process? Is there a way that we can potentially have a machines to potentially answer some of these questions? It turns out it's very hard. First of all, the data is very hard to get by, right? So in order to train this kind of machine that answer which pair of shapes is better, we need to get description of the shapes, the pair of shapes generated, and once we get that, we also need to have a lot of labels describing which shape is better. And what's more challenging is, what makes a 3D shape better? Like what criteria would you use to evaluate 3D shapes? Some people care about the shape, some people care about the texture, some people care about both, some care about functionality. So each of those, imagine, increase a row or column at the end. So this data collection process is very hard. So what we are hoping to do is we would like to leverage some of the existing reasoning power from vision language model. So the idea is we can take this pair of 3D shapes, and we already know how to render that into multi-view images. So concatenating all the multi-view image together gets you a larger image, which is a modality that vision language model able to understand. So can we poke them and ask the question, which 3D shape is better? This is our first try with GPT-4V, the next day that it released. So it's able to give some reasonable conjectures. I would say that they would say, oh, in order to evaluate which shape is better, they need to look at different criteria and gives a comparison of some is better than the other. But a concern still remains. Like, I mean, it might make a mistake. It still hallucinates about the reason. So here's one example of the hallucination. So this is a rendering of 2 shapes, and I crop the center part and send it back to ChatGPT. It suddenly changed its mind. So what we decided to do is like we want to tell first understand that GPT is a slot machine. So you add the points and then it will give you a random result. So fundamentally, it's a probabilistic model, and what you see is a sample from it, right? So and what we hope is to estimate the probability distribution from the sample, and then this estimator can encounter 2 sources of error. So one is potentially biased. So the idea is, if given 2 shapes, the human says X is better, but the GPT say Y is better. So this is basically the probability of one is better is kind of flipped relatively. But this is not the kind of things I can fix at that point, because that requires to fine-tune the model. But there is also another source of error that people seem to overlook, which is the variance. Because every time when we flip a coin, you think about this as flipping an unfair coin. So if the question is only 51% one is better, 49% the other, and even if that's the probability that human gets, you still need to flip a lot of coin in order to figure out which one is better, right? So this is the issue of high variance. So we make the hypothesis that potentially a lot of the error can potentially be leveraged, be mitigated if we are able to increase the sample size in order to estimate the underlying fair coin probability. So our solution is actually very simple. So the idea is we take a template of how we want to ask questions about ChatGPT. And we augmented the templates with different, we augment the templates. The AI is listening in the future. Yeah. So we augmented the templates with the image and text. So basically, we asked the same question in different ways. So the simplest augmentation is changing the random seed. That's basically a lot of people are doing, like by just asking multiple times. And then we collect all the results and find the popular votes. And it turns out that this method is very, very important in order for us to get stable statistics that's aligned with the human judgment. So this gives you an idea of how we compare two pairs of shapes, but how do we judge which 3D generative model is better? So what we do is we run a tournament. So we collect 13 3D generative models, and then we used our judge that I just described to you using GPT and augmented ensemble methods as a judge, and then we run pairwise games between all the models, and then we can collect a set of results of who's winning and who's not. And we use this result to compute a ELO score, which higher score usually indicates like better performance of the player. So we do the same experiments with humans, and here we show the score of how much the GPT's results agree with the human's result. So it turns out that we are able to achieve pretty good alignment results in most of the criteria. So remember, in the 3D evaluation, you need to ask different questions for different shapes and applications. So this is pretty impressive result, 0 out of the box. And the key thing is we can also, with this metric, we are able to take each of the 3D generative model and look at it in a more holistic way. The idea is like maybe that your performance of the model is not quite as good, but what is the axis that you need to improve? This is a question that a lot of developers are curious. So with our metric, you are able to give a more detailed view. So for example, in here, we show the top 4. Prolific Dreamer is actually doing pretty well, except for the possibility, 3D possibility axis. It turns out that if you look at the 3D shape of Prolific Dreamer, it has a lot of those high variant artifacts, which might not be quite as plausible in the real world shapes. So this gives you a hint on, for example, if you want to improve on top of Prolific Dreamer, that's the places you can work on. Okay. So I think the idea of this work is very simple. The idea is like if you need to run a lot of user study, you can pull, and a lot of those user study might be like high-level semantic and easy questions. You can potentially replace that with a carefully prompt visual language model. But this is just the beginning. But I think the idea of automatic user study or Turing test is also adapted to other places, including evaluate captioning and 3D editing. And it is a very important question that I feel the field needs to answer better. So at this point, I think you've seen how do one way that we can ask different questions to compare two shapes, which one is better. We were seeing one way to potentially create codes that can later put into the scene. How about we put these two works together in multiple iterations? What can we do? So the playground that we use is to do graphic editing in Blender. So the idea is that imagine that you want to edit the Blender texture nodes. This is the nodes that you would look at for some of the times. So which one do you want to go inside to edit? It's actually not easy. So wouldn't it be nice to have a text-driven copilot that helps you to decide how to change this in order to achieve the final result at the end? So in order to do that, as I told you, what we do is the following. So we take the Blender code together with the text instruction, put it into VLMs, and we need to prompt it carefully. And we instead of asking it to generate one version, I asked them to generate a couple more options. See here is 6 options. And then I take these 6 options to run a tournament, as I showed you in the prior works. And the tournaments will pick the winner. The winner of the tournament will be replaced in the beginning. And we do this process again until I run out of money or GPT credits. So here is some of the results. So each of the batch shows a batch of the edits. And the highlighted one is the champion of the tournament. So you can see that in Blender Alchemy, that this process, we are able to iterate between this process and finally picks one of the outcomes that aligns pretty well with the text input. And with this, we are able to try to do this with a more complex scene. So this is one very complex Blender scene that I added part of the texture. And here is another Blender scene where we change the texture of the shades according to the prompt. And this is not limited to changing the texture and material nodes. It can be also applied to edit other tasks. For example, here I shows that the Blender Alchemy is able to edit codes for geometric nodes. So it can change the geometry to create a flower blossom. And here I shows that Blender we can use this iterative process to change the shape key, which are a bunch of parameters that controls the geometry and of the face, and we can change it according to a text description that describes how you feel instead of how it looks like. So this. No, we render the 2D views. So the idea is like when we change the code, we render it in 3D, and then we render back the into 2D, and then the judge will look at the 2D views to decide which one is better.
But you don't have any automatic state. Do you use it like more like RLHF, like reinforcement learning and human feedback, or how do you use it?
Yeah, so I guess the question is how do we optimize for this process? So my technique right now is still PhD descent. So basically, we still need a lot of heavy prompt tuning, unfortunately, but it is an open question. So I think it's super important to be able to work efficiently to tune this VLM system. Actually, this is one of the future works that I want to mention, right? I mean, in the future, I envision there will be a lot of like this system that work with non-differentiable tools like in Blender. How do we optimize this system? I think is still some of the open question that I'm super excited about. So I think that concludes the kind of the 3 works I'm trying to I like to share with you, and I think this is a perfect segue into to describe some of the very exciting future work that I see from extending from this direction. So I think the field is still very young to build this kind of general, versatile AI that's able to understand spatial data. So there are ways to extend both answering the fundamental question as well as application questions. So I'm going to touch base on some of the things that I'm very excited about, and feel free to ask any question and make it a discussion. So the technique that I described is not limited to only in Blender, right? There's a lot of graphical software that you might use every day, like AutoCAD, Fusion, or even think about a real-world robot might encounter the same question. Might take advantage, might be benefit from the ability to synthesis by analysis. How do we kind of deploy this system to this other task? It's a very, very interesting question. And I believe that it's still very challenging to, in order to really deploy this system, we need to improve, like, for example, iteration speed and hard constraint. And all of those are touching the frontier of both machine learning as well as computer graphics. Just to give you an example, so this is what we were just discussed. So I think in the future, I envision that we might be building different models potentially that are good at different collection of tasks. But all of them are kind of trying to mimic the ability of like one user or operating on a set of tasks. But in order to build a very impressive scene and experience, think about like the Ubisoft company, like those company that's able to build amazing game experience. It takes a team and a village, hopefully, if not a village. So how do we build this like large systems that has this spatial understanding and is able to work together and optimize this system to perform well and operates like a company? That's, I think, is a very, very interesting work. So I take a little bit of the initial exploration. So the idea is like, okay, if we were given what we have right now, we don't have, even if we don't have the ways to optimize the system yet, if we simply increase the compute of that I put into the system in inference time, do we get some advantages? So here I shows that the x-axis increase the inference time compute by, like, for example, it makes more evaluation runs and more generation runs. The y-axis shows the performance of how close is the final scene to the ones that the artist would like. So we can see that increased compute does have some benefit, but the rate of increase is still very low. So being able to do this optimization is still very essential toward real world applications. And on the left, I show the graph of, like, if I use different configuration, how much compute do I allocate for the generator? How much compute do I allocate for the evaluator? Different configuration have different trends of improving. So this means that it is potentially a very interesting question to optimize the system rather than designing it, because different design will lead to different scaling behavior. Maybe go a more fundamental questions that I'm interested in answering is, I mean, right now I show you how to use code and image as the bridge to connect the other modality in 3D. But what is the best representation to achieve and channel the power of machine learning and graphics, right? I mean, there are a lot of other options that people explore in the field, like, for example, using neural network as a representation, using point cloud as a representation. So a lot of my PhD and postdoc works are focusing on exploring the possibility of different representations. And I believe that this is still an ongoing search for the community. And of course, the pipeline is just as good as is the weakest link. So in both the modeling as well as the learning side, there are still potentially weak links that we need to improve. For example, in learning side, I mean, we want to have, should we use 3D as another modality, or are we satisfied with inputting only image or tokens? What if we want to input 3D, do we need to increase the context length? Because a lot of 3D data are fundamentally very long context, but sparse. On the modeling side, I think a lot of the pipelines, for example, might not be very efficient. For example, I just mentioned that in this very long geometric processing pipeline, how you mesh in the beginning might affect the result at the end. So are we able to create a pipeline without meshing? All of that are very interesting questions, I believe, for the fields. And finally, you might probably talk to people in the industry, and people say, how about you just get enough 3D data that we improve? Well, if in the future we get enough 3D data, do we still need to worry about building this nice connection between learning and modeling and learns with limited data? So here's what I'm thinking. So I think that the current scaling paradigms is trying to, what they are trying to say is, if we increase the amount of resource we put from x0 to x1, we can get lower loss. So if you, so maybe one of the way to get better performance is just to keep pressing, getting more resource to it. But being able to understand and learn and do the learning smartly with even limited data, for me, is a new kind of scaling. So it's what I call a data scaling paradigms. So the idea is like we work with the resource that we have, but we change the slope. And I believe that this is going to be something that people are going to discuss quite a bit given the news of DeepSeek. And this is also something that I'm very excited to talk about as very fundamental questions that's important for not only spatial intelligence, but general intelligence. So finally, I hope that so today it's really my pleasure to share some of my works, and I hope that I give you the feeling that there's a lot more questions to be answered. And I would like to take the chance to thank my founding organization and collaborators. And I also do a lot of other works in the space of 3D understanding generation. I'm happy to chat more if you have any question about some of that. Yeah, thank you so much.
I have a question.
Yeah.
So when you compare the number of tokens or the amount of data we had to train the large language models versus these for potential for 3D engines, you use the number of 3D objects. But in your work, where you tokenize like garments, right? You show that with, you know, if you do tokenization properly, you actually have more tokens.
Okay.
So do you think that lack of data is really a lack of good tokenization strategy?
Great questions. So why do we compare one 3D shape with one word? Like maybe, so in my heart, each 3D shape worth 1,000 words. So the how to use a 3D shape well, I think is still a very active research. So, and in fact, if you are able to use the 3D training data well, you are basically taking this axis and diluting it in order to create a steeper scaling loss. So I do believe that is, I mean, that analogy is a little bit of non-considered, as like one shape might not be containing the same information as one image. And so I can, one thing that I'm very excited about with something on some of my ongoing exploration is like, what can we train with only one shape? So in fact, we are able to do a lot. So I mean, there's one work I'm trying to learn how to solve a PDE with on different geometry, and it turns out we find that we are able to solve it in one geometry, take the Green's function I learned, and apply it to all other geometries. So I think this field of how to leverage the 3D data well is also very interesting. Yeah, thanks for that question. Yeah. Okay. Other questions? Costa. Sure. Yeah.
A lot of people argue that because there is a lot of data in 2D, the best way to 3D is one of your.
Yeah. Right. So that is multi-view images the best way to understand 3D? I think it still has some of the limitations. Like, for example, it's not probably the very token efficient way. So imagine that in order to reveal internal structures, then I need to choose, like, for example, how to render it in order to reveal all the fine details, or maybe I need to slicing it. So all of this decision already use some of the 3D reasoning, right? Where does that information come from? So right now, I think that even in some of my works, that information comes from us, because we know how to place the camera. We know that we probably need to take the slice in order to look at the internal shape of the 3D. So, but that's probably hopefully a potential answer it's not enough, right? Because we still need to inject additional 3D information to decide where to look at in order to create multi-view image to cover the same information. So I think that is still a unsatisfactory answer. But the reason the multi-view image is attractive is because it connects very well with the huge amount of data that we have. So I mean, the reason that I asked the question of how to connect the power of machine learning and modeling is because there are different things, different community ask for different things for the representation. For machine learning, we care about scalability. We care about how close is it to the source of the data. I think that's probably where multi-view image are winning a little bit. But in 3D, we also care about all the other things, like are we able to handle topology well? Are we able to handle thin structure well? I mean, all of those, and localization, like where do we place the camera? That seems to be some of the harder question that might not completely answer by if we only work with multi-view images. I mean, there might be potentially ways to fix that, but basically there's a very interesting trade-off on like whether we slice more toward the left side and say, okay, this is what we want to compromise for, or whether we slice more to the right side. I think multi-view image is very much the left side representation. Yeah. Question?
Did you look at evaluation over the code, like the underlying code? Because I mean, you do the generation in code, so why don't you have you looked at it?
Yeah, very good question. So why do we need to render it into image and then do the evaluation? Why don't we just take the code and then compare, look at it? So here's the thing. So if we look at a code in Blender, it say that some shape key of 1.3, 1.4. What does it mean? Like, is 1.3 better or 1.4 better? So most intuitive way to look at it for us, or at least for me, is we render it and look at which ones makes the reasonable change. So numbers means different things in different software, especially in the 3D applications. So that's why I think it's very important to render it into codes. We do compare to one of the baseline that compare only code, not image, and they are not able to like handle all this nitty-gritty detail very well. Yeah, and one of the other nice advantages the following. So imagine that you train your agent in Blender 1, and then you want to test it in Blender 4. I mean, all the API might be changed. So how do we know? Like, but if you imagine that if you were the customer with expert on Blender 1, and then you suddenly need to code Blender 3 or 4, you are able to just twist the parameter a little bit and look at what it produced, and suddenly you are becoming potentially very quickly the expert on Blender 4. So being able to render the image and understand the grounding between code and the 3D is very essential. Yeah.
Is GPT able to work in Blender 1 and Blender 4?
Yeah, so think about if how do GPT understand the difference between Blender 1 and Blender 4? So potentially they scrape a lot of data online. Some of them has metadata like Blender 1 code look like this, and then has an image, and some of them has Blender 4 codes that look like this. Is that even if that's a huge chunk of data that the GPT is able to learn, I don't know whether that's significant enough for them to understand all the nitty-gritty. But for this application, you need that little difference matters a lot, right? So I think it's better for us to actually run the code.
So that means you, for like a geometry change, you prompt it to specifically only work in the geometry space of the Blender code, right? You don't like have it generate the entire Blender file.
Yeah, so how do we handle the Blender file, which is a super long file? It's a very interesting question. So it turns out that at the points of the GPT-4 when we are experimenting with it, they still might not have a very long context length. So we can't fit the whole Blender file in and output it. So what we do is like we first ask them to identify where to edit and then edit it. Yeah. Costa?
You're the Mr. Point Flow.
Oh, yeah. I'm happy to talk about that.
What do you think about like regarding 3D? Dead,
oh, yeah.
The actual technique of generation.
Right. So I mean, this is related to one of my past work in point flow, which use normalizing flow to generate 3D point clouds. And I think I think there are a couple of things that I've still liked about point flows. That's something that I've been thinking a lot about. First, I actually like point cloud as a representation a lot because even though it's irregular, but it's very flexible. So, and it's also potentially close to the source of the data, right? So potentially, and it works really well with transformer. Think about what is transformer. It's a set to set function. Point cloud is a set of points. So I think it is actually fitting pretty well in this category. And as for what is the best way to generate point cloud, so is normalizing flow a good way or not? So the part that I'm very concerned about normalizing flow is we need to normalize the computer normalizing factor of the distribution. And this is something that I don't feel necessary in order to capture the geometry. So in my other, so the idea is that if you think about a probability density field, you multiply the field by 10, it would still show the same shape, but it would not be a normalized distribution. So I think that later on, I'll have some works on using diffusion model to model point clouds. And then there is also recent works on basically using probability distribution as a representation of shapes, but using diffusion model and rectify flows to model it. I think all of that, I think, kind of aligns with the spirit of point flows, but with a more better technique today. But I think that point cloud is a representation potentially fit very well here, and that's still worth exploring. Yeah. Question?
Any one particular point estimation model like depth flow or the depth anything now. And but based on my like test, if we use in the real world, like we use real sense or that, their point cloud is kind of very crash because you need to do this in real time and the rendering is not that bad. That's not good. So like, what do you think is the opportunity we'll have if we have some kind of like molecular estimation model, and how can we do this in 3D representation? Like we need distill knowledge from that model.
So when you say molecule representation, you don't mean the molecule in very like small particles, right? You mean? Yeah. Oh, I see. Oh, I see. So single view depth estimation, like right now we have very good single view depth estimation. What kind of chance can we get from it? And I think one thing that I like about single view the depth estimation is like it can be applied to different viewpoints. So you are able to apply it to video and image, and it's able to get very sharp features. So I think it's very exciting. But I think one of the issues that comes out is like consistency and how does that align with the real 3D, because depth is what's important in depth is like whether it's front or back. The relative is more important than the absolute scale. So what kind of application can we get away with the relative? I would say going with the depths would be pretty good. But if you really need the final nitty-gritty of like the final centimeter, I think depths might get us somewhere, but not the whole way. Yeah. But I'm happy to chat more. Yeah, because I think we're on time. Maybe last question. Yeah. Mm-hmm. Mm-hmm. Mm. Mm. Okay. Yeah, good question. So how do we do this? How do we scale better with a data efficient way? So a couple of things. What I show here is that you can leverage foundation models, so which are trained on different data. So they are not the data that plot in this axis, but they kind of like have a discount rates coming in different ways. So that's one way. The second way, there are many other ways that we can talk about. The second way is like, for example, we can study how much we can get to, how much we can do to train one single shapes by data augmentation. So this is one other way. And potentially you can include inductive bias for the models or the loss function. I usually prefer adding inductive bias in the loss function because in that case, I can still use the biggest and best models and potentially leverage some of the, without going to overfitting regimes. But I'm happy to chat more on that, but this is a very good question. Yeah.
Thank the speaker.
Yeah, thank you.